Good evening and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Dmitry Bankov. Dmitry is a senior researcher at the Institute for Information Transmission Problems, a junior researcher at the Higher School of Economics, and a lecturer at the Moscow Institute of Physics and Technology. He has authored more than 25 articles and received Best Paper Award at IEEE PIMRC conference. Dmitry, the floor is yours.
Thank you, Vyacheslav. So let us start. Today we will talk about MCS allocation in heterogeneous LoRaWAN networks. So LoRaWAN is a low-power wide area network technology designed for such scenarios of Internet of Things like wireless sensor networks. So it's specializing on scenarios where numerous end devices such as sensors or meters, we will further call them modes, gather some data, and they have to send this data to a network server. And a typical LoRaWAN network has a star of stars topology. It consists of a network server, which is a brain of the network. It controls the network and gathers the data. And this network server is connected to gateways. And the connection between network server and gateways is made via a reliable link, for example, Ethernet. And gateways act as relays between end devices, modes, and the network server. And modes send their data using a wireless link to the gateways, and gateways send this data to the network server. So gateways act as relays. In the wireless channel, the channel access usually in the LoRaWAN networks works as follows. So the network operates in several main frequency channels. For example, we have 3 main channels on the slide. And the network also uses a service downlink channel. So when a mode wants to transmit its data to the server, it randomly selects one of the main channels and sends its data in this channel. After the time T1, after the end of mode transmission, the mode opens a receive window, and during this receive window, the server has to send an acknowledgement to the mode in the same main channel. And also, after the time T2, after the end of the data transmission from the mode, the server, the mode also opens another receive window in the downlink channel, and the server can send an acknowledgement also in this downlink channel during the second receive window. And typically T1 equals 1 second, T2 equals 2 seconds. It should be noted that data frames in LoRaWAN networks are usually can be rather long. For example, at the slowest modulation encoding scheme, a data frame can last from 1 second to 2.4 seconds. So these values are comparable with T1 and T2 values. And acknowledgements are just data frames with an acknowledgement flag turned on. So the channel access in LoRaWAN networks is a kind of aloha channel access, which uses several channels and where we have acknowledgements. Okay, so as I said, if a end device mode does not receive an acknowledgement from the server, it has to make a new transmission attempt. For that, it selects a new main channel again, and also it has to wait a random delay, which is selected from the window from 0 to 2 seconds. So it is an important issue because these 2 seconds are comparable to the duration of a frame at the lowest MCS. So let us move on. On the phi level, LoRaWAN networks use a modulation called LoRa. It is a kind of a chirp spread spectrum modulation, which works as follows. So a device transmits signals which have a frequency which linearly changes with time. So, for example, this is the bandwidth which the device uses for data transmission, and it transmits a signal which starts at one part of the bandwidth and moves slowly to the upper part of the bandwidth. And the values of different symbols are encoded by the offset at the beginning of the symbol from the edge of the band. For example, different symbols have different offsets, as you can see on the slide. And the LoRa modulation has a parameter called spreading factor, which determines how quickly the signal covers the available bandwidth. So it determines the symbol duration. And as you can see on this slide and in this formula, the symbol duration is 2 to the power of spreading factor divided by the bandwidth. So if we increase spreading factor by 1, we make symbols 2 times longer. And different modulation encoding schemes in LoRaWAN use different spreading factors, and different signals with different spreading factors have different bit rate. The higher the spreading factor, the lower the bit rate, but higher spreading factors also mean better receiver sensitivity and better possibilities to cope with noise in the channel. And the modulation encoding schemes that can be used by end devices are assigned by the server according to some algorithm which is not specified in the standard. So it is implementation dependent. And also, when the server sends acknowledgements in the downlink channel, it uses the same MCS for all frames, usually the minimal one. Also, acknowledgements which are sent in the main channel are sent by default. They are sent at the same MCS as the data frames, but optionally, an offset in MCS can be configured. So we can send acknowledgement at an MCS, for example, by 1 or by 2 lower than the MCS used for data. And modulation encoding schemes used in LoRa have a peculiarity that signals with different spreading factors are almost orthogonal to each other. So if we receive from the channel 2 signals simultaneously, for example, the blue signal transmitted at 1 spreading factor and the second signal, the green signal, is transmitted with a spreading factor +1, we can receive both signals simultaneously. So as an illustration, if we have a sum of signals here, and if we multiply this sum of signals by a complex conjugate signal, we obtain a blue signal, which will be a signal at a constant frequency. So we can filter out this signal. And at the same time, if we implement it by another complex conjugate, which corresponds to another spreading factor, we obtain another signal at a constant frequency. So in an ideal situation, we can receive several signals which are transmitted simultaneously in different frequency, in the same frequency band, if they are transmitted at different spreading factors. So spreading factors allow us to virtually organize several orthogonal channels in the same frequency band. and we'll be able to receive several signals simultaneously. For example, we can use this feature by assigning different spreading factors to different modes, and by serving these modes at the same time. Another important peculiarity of LoRa signals is the capture effect. So even if two signals are transmitted at the same spreading factor in the same channel, their intersection in time does not always lead to the loss of both packets. If one packet is much more powerful than another one, then the more powerful packet can be received successfully. And existing papers report that if the difference in the power of signals is more than 3 decibel, then we can recover the more powerful signal. And these two features are very important for the study, which I will tell you about. So let us consider the following scenario. We have a LoRaWAN network, which consists of a gateway connected to a server, and around this gateway, in a circle with radius of r kilometers, we have n modes, and these modes are spread uniformly within this circle, and they are divided into G groups, and we know the sizes of each group, and modes from these groups, they generate Poisson flow of packets. And modes from different groups generate Poisson flows with different intensity, lambda G. And the gateway, the network server assigns different modulation and coding schemes to these modes. And the network uses F main channels and one downlink channel. And we assume that signals with different spreading factors are orthogonal. And we have capture effect. So if two frames are sent simultaneously and one frame is at least by Q decibel more powerful than the interfering frame, then this frame is received successfully. So given this data, input data, we all have a requirement that the packet loss ratio for all modes from group G should not exceed the PLR QoS G. So for every group of modes, we have some specific requirement on packet loss ratio. So the question is, given the number of groups, the number of modes in each group, and the load generated by modes from different groups, and the PLR requirements, how should we assign the modulation and coding schemes to the modes from different groups in order to provide the PLR less than the required values? So how do we satisfy the quality of service requirements? So we have developed a solution to solve this problem. Let me start with a description of this solution, but firstly, we need to, let us find the packet loss ratio for devices in the LoRaWAN network. So we have developed an analytical model which can help us find the PLR. So let us consider one mode which uses MCS number I. And let us find the probability of this mode to send its frame successfully. So this mode transmits its frame successfully if it either makes a successful transmission attempt from the first time, or if it makes an unsuccessful transmission attempt at its first attempt, but during its retransmission, it makes a successful retransmission attempt. Or it makes a an unsuccessful transmission attempt from the first time and from the second time, but the third time it makes a successful retransmission attempt, and so on. It can make up to retry limit retries. If we consider the network in general, I mean, not only one mode which uses MCSI, but all possible modes from the network, we have to use this probability of successful frame delivery and to combine it given the portions of modes which use different MCSs. So here in square brackets, we have a P success value. And we also introduce the PI value, which is the probability that a mode uses MCSI. Or it is a portion of modes which use MCSI. For example, these portions are set by the gateway when it assigns the MCSs to different modes. And if we calculate 1 minus this value, we obtain the packet loss ratio for modes in the considered LoRaWAN network. So this equation consists of several values which we have to define. And let us talk about PS1, which is the probability of modes making a successful transmission at first attempt. So mode makes a successful transmission at its first attempt if it sends a data frame successfully, which happens with probability P data I. And after that, it receives an acknowledgement, which can be either an acknowledgement in the main channel or in the downlink channel. So let us find the probability of successful data transmission. And for a while, let us assume that we have only n modes, which generate lambda frames per second. And as I said during the scenario description, we assume that modes generate a Poisson flow of frames. So in this situation, we can use an approach, a typical approach of modeling asynchronous Aloha networks to find the probability of data frame being transmitted and not intersecting with any other frames, which is written here. An exponent to the power of -2 t data plus p data TAC plus a fraction. Yeah, so this value here is the probability that given the Poisson flow of data frames, we transmit a data frame from mode 1, and in the interval with t data, which is the data frame duration at MCSI, there are no frames generated by any other modes which could collide with the considered frame. And also, we consider the situation when another mode could transmit its frame before the considered one. And after this successful frame, the data from mode 2, the gateway has to transmit an acknowledgement to this frame, and this acknowledgement can collide with the data frame. So both of these situations are described in this exponent under the assumption of Poisson flow of data frame transmissions. But this here is the situation when the considered frame does not intersect with any other frames. So it will be delivered successfully in this case. But also, as I said, we have capture effect in LoRaWAN networks. And so if we have some mode which transmits its data frame during the considered frame transmission, we still have some probability that the considered frame will be received successfully. And we take this situation into account in this sum. So here we sum over the number of frames which can be generated during the data frame transmission, T data. And with this probability, which is which is described by the Poisson distribution, we have k frames generated during the data frame transmission. And we also introduce a v value, which is the last multiplier in this sum. The last multiplier stands for the probability of frame to be received successfully, provided that it intersects with k other frames. So this is the probability of capture effect to actually happen and to help us retrieve the frame successfully. Now let us find this v multiplier. And to find this multiplier, we have to assume some path loss model and the mode distribution model. So the mode distribution model, we stated it in the scenario description. It is a uniform distribution around the gateway, and the distance from the mode to the gateway is described like rho and shown on the slide. And we assume a log distance path loss model, for example, Okumura-Hatta model, or some other empiric model which describes the LoRa links. And in this paper, you can, in the paper shown on the bottom of the slide, you can find some empiric models which have been measured and described specifically for LoRa links, but they are also log distance. So in this model, the power of signal at the receiver, at the gateway, depends depends on the distance as a constant minus a constant multiplied by the logarithm of distance. And this power is measured in decibel per milliwatt. And yeah, so given this path loss model, we can find the probability of capture effect. And to find it, we consider the following situation. So we have a gateway in the center of the network and the mode situated at the distance x from the gateway, so mode 0. And it's situated at the distance x from the gateway. And then we consider possible locations of another mode in this circle and find the probability of this mode to be far enough from the gateway so that the power of the received signal from mode 1 is less than the power of the received signal from mode 0. It is less than this power plus q decibel per plus q decibel, and we can find this probability as a function of x, and as shown on the slide. So yeah, so it is given as in this formula. And as we can see, this probability depends on x, the distance of mode between the mode and the gateway, and it depends on the parameters of our path loss model, C2 constant, and it depends on the capture effect parameter Q. So we had this formula for probability of successful data transmission, and now we can simplify this formula. On one hand, we can simplify it, and on the other hand, we can make this formula more general, assuming that we have several groups of devices which generate several different intensity of frames. And this is what we do here. So first of all, we change V. Instead of just v as a constant, we set v as a function of x, so it's now a function of the distance. But also we simplify this sum by leaving out of consideration all the summons higher than 1. So we take only the summons k equal to 1, and the remaining summons we don't take them into account because they correspond to much less probable events when several devices at the same time generate their data frames. And also here we, instead of lambda, the total intensity of data or total intensity of traffic generated by all modes, we put here the intensity of data frames generated by modes from different groups, but which are assigned to MCS equal to I. So we consider only a single MCS I. And here we introduce the value Li, which is the total load generated by modes assigned to this MCS. So thus we obtain the probability of successful data transmission at first attempt at MCS I and for group G. And it is a function of the distance from mode to the gateway. Well, in a similar way, we can obtain the probability of successful acknowledgement transmission. The formula for successful acknowledgement transmission is similar to the data transmission. It just has different data frame durations, so I do not write it here. And also in a similar way, we can find the probability of successful frame transmission during a retransmission attempt, but there are some peculiarities related with the random Bankov weighting by the modes. And for more detail, please read this paper shown on the bottom of the slide. It is published in open access. Yeah, so in the end, we can obtain the PLR as a function of the distance between the mode and the gateway. And we have a PLR for different MCSs and different groups of modes. And in the end, if we consider some specific distribution of mode distance to the gateway, we can find the PLR distribution in the network, like shown on the slide. So we integrate over this distribution and consider only the values of PLR which are less than some value y. So let me show you some numerical results related with PLR distribution in the network. And as you can see here, for example, in this scenario, we consider one group of devices. There are 1,000 modes in these groups, and they generate 0.5 frames per second. And for simplicity, we assume that they use only MCS 5, which is the fastest MCS. And in this case, we obtain the following dependency of packet loss rate on the distance between the mode and the gateway. As you can see, it grows from 0 to some value. And at this value, it reaches a kind of a step. And from this value, it is almost constant, or maybe very slowly decreasing. So what we obtain here is that modes which are closer to the gateway, they have lower packet loss rate. And modes at the edge of the network, they have the highest packet loss rate, which is quite logical because if modes use the same transmission power, then the power of modes close to the gateway is much higher than the power of modes which are on the edge of the network. So the probability of the capture effect will allow the modes which are close to the gateway send their data successfully. And thus we see that the capture effect creates some kind of inequality in packet loss rate distribution. So if we use this dependency together with distribution of mode distance from the gateway, we obtain the following CDF of packet loss rate, as shown on the right slide. So we see that it grows almost linearly, and then it reaches some sudden increase. And this is an important result because, as you can see on the slide, we have the average value, which is a pointed line. A vertical pointed line is the average PLR value in the network, but almost half of the modes, they have the highest PLR value. So we have very significant inequality of PLR distribution, which is actually caused by the fact that the number of modes close to the gateway is smaller than the number of modes which are far from the gateway. So it is an important fact that when, for example, if we want to consider the PLR, if we want to assign MCSs to provide some PLR guarantees, we cannot take into account only the average PLR value, but we have to consider the PLR distribution, for example, some high quantile of PLR or the maximal value of PLR, which can be significantly higher than the average value. And yeah, and also we see that the start of the step on the left plot is parameterized by the capture effect parameter, and we can find it with the formula shown on the left plot. Yeah. So let us now use this analytical model to assign the MCSs to devices. For that, let us introduce some additional value, which is the maximal PLR corresponding to group I, to group G at MCS I. And we take the maximal value of PLR for all possible mode distances from the gateway. And it is also a function of total intensity of traffic from all modes, and it is also a function of intensity of traffic generated by the modes from this group, by one mode in this group, and it is a function of load generated by all modes that use the given MCS. So it depends on three values. We can define an auxiliary value. For example, the maximal load, which is generated by devices which use the considered MCS I. And the maximal load at which the PLR requirement holds for group G. So we have different PLR requirements given by different groups, and for every group we have some specific maximal load which can be assigned to the given MCS, and if we assign more devices to this MCS, the PLR will be higher than the required value. So we will call this value the network capacity for this group and for this MCS, so mu GI. So it is the maximal load which yields PLR lower than the quality of service limit. And let us use this value. We use this value to in our algorithm, which assigns MCSs to devices from different groups in a way to guarantee that their PLR requirements are satisfied. So this algorithm has the following scheme. I will show you an example of this algorithm operation. It will be easier to understand how it works. So it has the following input parameters: the number of devices in each group, the load generated by each device in each group, the maximal, the PLR requirements by each group, PLR QoS, and the capacity per MCS per group. And this capacity is calculated using the analytical model, which I described in previous slides. So the idea of this algorithm is to sort the devices of different groups by their packet loss ratio requirement. We sort these devices in the ascending order. So we firstly consider devices which require the lowest PLR, which have the strictest requirements of PLR. So we start with such devices, and we start with the slowest modulation encoding schemes. Slowest modulation encoding schemes, they have the lowest capacity because frame durations at these MCSs are the longest. So yeah, like that. So we start at the slowest MCSs and with the strictest PLR requirements, and we start assigning devices from this group to the slowest MCSs, and we do it until we reach the capacity at the considered MCS for this group. And if we reach the MCS capacity, we proceed to the next MCS, a bit faster MCS, and assign this MCS to devices from the group. And we do it until we run out of devices from the considered group, and then we proceed to devices from the next groups, which have less strict PLR requirements, and so on. And to be to make it easier to understand, let me consider the following example. We have 3 groups of devices. One group consists of 10 modes. The smallest group, each mode generates 10⁻⁻⁴ frames per second, and they require PLR less than 10⁻⁻⁷. So we have a very small group which have very strict PLR requirements. We have group 1, which consists of 100 modes, which require PLR less than 10⁻⁻⁶, and group 2, which consists of 1,000 modes, which require PLR less than 10⁻⁻⁵. So the number of modes, the generated load, and the PLR requirements are given in the left table here, and on the right, in the right table, we see the capacity calculated for devices from each group for each MCS for each group and for different MCSs. So here we see that, for example, group 0, it has the strictest PLR requirement. So the capacity for this group is the smallest. It is the smallest, and with the increasing MCS number, the capacity also increases. Yet, and yes, and for the other groups, we have a higher capacity, which increases with the PLR requirement and with MCS number. So firstly, our algorithm starts with MCS 0 and with group 0. It tries to assign devices to MCS 0. So we take one device from group 0 and assign it to MCS 0. When we do it, the rate of the traffic load at MCS 0 will be equal to 0.0001 frames per second. And if we add one more mode to this MCS from this group, we will have the load which will be higher than the capacity. So we do not do it. We leave only one mode in this group. And at this MCS, and proceed to MCS1. At MCS1, we consider, we try to add devices from group 0 to this MCS. And if we add 2 devices from this group, we obtain the load 0.002 frames per second. And we cannot add more modes to this group, to this MCS, because we will exceed the capacity. And in a similar way, we proceed to MCS2. Here we can add 4 devices to this MCS. And the remaining devices, they go to MCS3. So 3 devices from group 0 go to MCS3, and they generate 0.003 frames per second. And then we run out of modes in group 0 and move to group 1. At group 1, we ended at MCS3, so we continue at this MCS. So for group 0, we have a capacity equal to 0.0007 frames per second. This is the capacity at MCS3 for group 0. So the 3 modes which have been assigned to this MCS, they generate 0.003 frames per second. We can add some modes from group 1. For example, if we add 4 modes from group 1, they will generate, in total, they will generate 0.007 frames per second. But if we try to add 1 more mode from group 1 to MCS3, we will exceed the capacity for the modes from group 0. So we cannot add any more modes from group 1 to this MCS. This is why we do not add any more modes to this MCS and move to MCS4. And at MCS4, we can assign all remaining 96 modes from group 1 to this MCS because the capacity is higher than the load which will be generated by 96 modes, like this. So we have some remaining capacity at this MCS. It is 0.0132 minus 0.0096 frames per second. We can add some modes from group 2 to this MCS without violating the capacity for group 1. And then we can move to group 2 at MCS5 and assign the remaining modes to this MCS. And in the end, we obtain the MCS assignment, which satisfies the capacity limits by all groups at all MCSs. And thus, it satisfies the PLR requirements for all groups. So if we see here, the maximal packet loss ratio per MCS, it is less than 10 over minus 7 for MCSs where we have modes from group 0, MCSs 0, 1, 2, 3. And for MCS4, we don't have any modes from group 0, but we have modes from group 1. And here, the maximal PLR is less than the 10 over minus 6. So we also satisfy the PLR requirement for this group. And for MCS5, we have PLR less than 10 over minus 6, less than 10 over minus 5. So we also satisfy the PLR requirement for this group too. And yeah, as you can see, we satisfy the PLR requirements for all groups. At the same time, here we calculated the capacities according to the formula which uses the maximum PLR value here. But if we take into account only the average packet loss value, packet loss ratio, and assign the MCSs according to the average PLR, trying the average PLR not to exceed the PLR limits. then it is possible that we will the maximal packet loss ratio in this group will exceed the requirements imposed by some groups, for example, here. So this is what happens if here, instead of maximum, we take the average of PLR over all modes from the distance from 0 to R from the gateway. So this is why it is important to take into account not only the average PLR, but also the maximal value, so that we can provide the PLR values for all devices, regardless of their distance from the gateway. So for the devices close to the gateway and for the devices at the edge of the network. And so that's it. So we have developed a mathematical model which can be used to find the PLR distribution in a LoRaWAN network. And it can be used to describe a heterogeneous network, which consists of different devices, which generate different intensity of traffic and have different PLR requirements. And we have shown that the capture effect leads to such a result that the packet loss ratio is spread non-uniformly within the network. So modes closer to the gateway have more favorable conditions than the modes at the network edge. And we have developed an algorithm which uses the developed mathematical model to assign the MCSs to the modes in order to satisfy their PLR requirements. And that's it. So for more information, please, you can read the following papers. The first paper is available on Archive, and the second paper is published in open access, so they're available for reading. And I will be glad to answer your questions. And I see several questions in the chat. Let me start with these questions. Artem Krasilov asked me if it makes sense to assign different frequency channels to different groups with different PLR QoS requirements to balance load in different channels. In case of LoRaWAN networks, I think it has more sense to assign. I think it has more sense to use to balance the load by MCS than by channels, because we usually have the number of channels can be less than the number of MCSs. So we have more space for optimization if we balance the load by MCS. And also, the standard states that devices use the channels. They use the available set of channels and select them randomly. So I don't think that by the standard we have an opportunity to assign the different channels to different devices.
Just one comment. So you said that the number of frequency channels is less than the number of MCSs, or maybe I understood something wrong. So which is the typical order of the number of channels available?
Well, by default, for example, in European standards, by default, there are 3 frequency channels, main channels. And the other channels they can be supported, they can be not supported. So there can be 3 channels or more channels.
Okay.
And so the number of MCSs, in the worst case, the number of MCSs is more than the number of channels.
Okay, thank you. Because for other technologies, I have the knowledge that hundreds or thousands of frequency channels is used, so it's more typical situation that you can spread the load over the frequency channel. So if really that happens for LoRaWAN, that's my question is this answer. Thank you.
Well, maybe we can combine both approaches, like to spread the load over MCSs and over frequency channels, and like that.
Okay, thank you.
Andrei Belagayev asked whether the Q value depends on the selected MCS of the packets in collision. Well, I think it might depend on the selected MCS. It's just some value, the 3 decibel value is given in the datasheet of LoRa devices, and in the datasheet it says 3 decibel for all MCSs, for all spreading factors. But maybe in if we don't consider only the datasheet but measure it in real devices, it can provide some difference between slow and reliable MCS and fast and less reliable MCSs. So in general case, we might assume that Q value depends on MCS, and in this formula here, we could use Q, which has the index I, for example, to take into account that we can have different Q for different MCSs. Yeah, so we still can use this model, we just have to add another index here. And Mikhail asked if in the considered example, you distribute the MCSs assuming that their position is the mode's position is random. You set MCS and only the distribute modes over the cell. In practice, you could take into account the actual channel gains for a particular mode distribution realization. Would it be more efficient? Well, perhaps we could, for example, take we could take this packet loss rate curve, and we could find this curve for different MCSs, and we could assign, for example, MCSs in a kind of ring structure around the gateway, like modes close to the gateway will get MCS 5. Next modes will get MCS 4, 3, and etc. But we try to do it, and well, sometimes it is inevitable that you have to design, you have to use some MCS because you cannot use a faster MCS. For example, if a mode is very far from the gateway, you can use only a slow and reliable MCS, but cannot use very fast MCS. But in case when you have a choice, for example, in this scenario, we chose the radius of the circle 600 meters, which can be used by all MCSs within the circle. In this case, if you for example, if you have two modes which use the same MCS, one is far away from the gateway, one is close to the gateway. If their frames collide, you still can receive successfully one frame from these modes. But if you concentrate all these modes at the same distance from the gateway, if their frames collide, there is a very low probability that capture effect will help you receive the data. So, for example, our numerical results, well, not shown on the slides, but we have some numerical results which shows that if you have an opportunity, you should better shuffle the modes within the circle, and I mean shuffle the MCSs assigned to the modes within the circle, and not sort them by the distance. So in this case, you can use the possibility of capture effect, and without it, you lose some part of the network throughput because capture effect doesn't help you. I hope my answer is clear, and if not, please ask me questions. I'll be glad to answer.
Well, thank you. Your answer is rather clear. However, I would like to clarify some more issues. So first of all, I meant a bit different point. For example, in your, as far as I understood, in your example and in your scenario, yeah, you assume that you assume that you do not have, do not know the locations of the modes, and therefore you will assume the worst case, as far as I understand, according to the maximal pillar. Yeah, you will assume the worst case that the mode is located far away. Each next, let us say, each next added mode is located far away from the cell. In some way. I mean, of course, you have a kind of general optimization. However, when you say that you use this model to build an algorithm and to assign MCSs, then you somehow assign MCSs one by one, and then adding some mode, you assume that, okay, it is located somewhere far or in an inconvenient position for the optimization for the problem. And if we could look at this problem from the other point, if we knew that we have these locations. Okay, no, actually, I maybe clarify this question in this way. So maybe I didn't get, but how do you, does your algorithm include the distribution of, well, no, not this way. So in fact, if you have a small number of users in the first group, in the group with the highest required PLR, will it be actually okay to assume that they are placed randomly, or in fact your model assumes that they are located just at the edge of the cell, and that's enough?
Okay, so I understand. So you're asking if we could use the actual distribution of modes within the circle to not to consider only the maximal PLR, but to use the distribution to provide a better, more complex, for example, assignment of MCSs. And
to take into account the actual position of these modes. So in this way, you said that, sorry, maybe I can clarify better. So in this example, you said that a single mode gets the MCS 0, then two modes get MCS 1, and etc. However, do you consider which of the modes will get which of the MCSs from the same group?
Well, in this algorithm, we don't consider this. We do not consider the position of mode in the network. So perhaps we could introduce one more dimension of optimization, like to consider the distance from the gateway to the mode while assigning the MCS to the mode. But well, we do not do it. Perhaps it might be done. It requires some further studies. We might we might consider, for example, not the maximal PLR, but some quantile of PLR given the distribution of modes within the circle. So instead of this utility function, we could use some other function to calculate the capacities. And here, while assigning the MCSs to modes, I cannot say at once which will be the best approach to assign MCSs to devices. I mean, if we know that, for example, one mode is far from the gateway, and the second is close to the gateway, and which will be the best way to combine them within the same MCS. Because, as I said, for example, when we know that one is far and one is close to the gateway, we can exploit the capture effect possibility, but if they are at the same distance, or we don't know their distance, we cannot do this. So I think it requires some further studies.
Yeah, thank you very much. I mean that maybe it might be interesting because well, it's clearly there seems to be another room for optimization actually. And,
yeah. So one more dimension for optimization and some better results.
Yeah. And just finishing the question, and how did you do this in simulations?
What do you mean? How did we calculate the assignment, or?
Yeah. How did you map the assignment of the MCSs to the group to the actual modes? So was it a kind of random, or?
Yeah, we did it randomly.
Okay, thank you.
Okay, are there any more questions? I'll be glad to answer them.
Have you considered power consumption of modes in your algorithm? Because as I understand from the example, you assign MCSs from the lowest one to the highest one. And if you have a low number of devices in your network, none of them use higher MCS, the highest MCS, as I understand. So could you give us some comments on this question?
Yes. In fact, yeah, it might be a problem that if we have few modes, they will all use the slowest and most reliable MCSs and will not use the fastest MCSs. Well, so this algorithm is designed for networks with big numbers of devices, actually, and we had the considerations that slow MCS, they have very low capacity, and we start with these MCSs because if we assign such an MCS to a mode from a group which is very demanding, it requires very low PLR. Then the number of modes which can be assigned to this group, even for example, if we use all the modes from group 0, for example, and move to group 1, the number of modes which can be assigned to the group will be very low. So we start from the slowest MCS because we know that there will be very few modes in these groups. And in case of few modes, I think we will have to make some renormalization. For example, if we see that some MCSs are not used, we can move some modes to these MCSs, and in order to optimize some other parameters, like you said, energy consumption. Because, well, on one hand, energy consumption is bound to the packet loss rate, because if a device makes unsuccessful transmission attempts, it has to make retransmissions, and it will lose more energy on one hand. But on the other hand, if a device can use faster MCS and it will be reliable enough, it should better use faster MCS, because signals at this MCS will have slower, shorter symbols and shorter data frames, and they will require less energy to transmit. Yeah, so we just didn't optimize the energy consumption in this scenario. But I think to optimize energy consumption, we might consider some renormalization procedure to move modes from slow MCSs to faster MCSs. Yeah, I think it might be a good idea for some research.
Okay, thank you.
Thank you.
Can I ask?
Of course.
As far as I understand, when a packet comes to a mode and there is another packet which is on retransmission, then this mode should drop this retransmission and start to transmit new packet. Am I right?
This is what we assume when we develop our mathematical model. So in general case, it is not always true, but we assume it because we consider that modes have short buffer, and it just persists to transmitting another packet.
Okay, maybe then there is an obvious dependency on the performance of the algorithm on the heterogeneity of the load that is provided by each group, because when the load is high, there is a high probability that they'll become new packets to the mode, and then it increases the probability of dropping the retransmission. So maybe it will make sense to send retransmissions on more robust MCSs, and then for example, for high-loaded groups, use more robust MCSs that will help to increase the probability of successful transmission of a transmission and decrease the probability of dropping of it.
Well, this is not a simple question, because on one hand, if you use a more robust MCS, then you achieve better performance while coping with random noise in the channel. But if you use slower MCS, your packets have become longer. So, for example, if you increase spreading factor by 1, your packets become almost twice longer. And longer packets means that there is higher probability of collision. And if you, for example, if you see that you make a collision and you want to make a retransmission, but if you decrease the modulation encoding scheme, you use a slower MCS, you thus increase the probability of one more collision. So in the end, it might not be very good for. It might not yield very good performance. And in case of high traffic load, high traffic intensity, it is more important to have a low collision rate than to have good performance against the noise. So in case of high traffic intensity, it is better to assign faster MCSs to decrease the collision probability, actually. But if you can distribute the MCSs between devices so that some devices will use fast MCS and other devices which will use slower MCS, but they will not collide with each other, so you will reduce the contention for the channel. You will increase the network performance. Yeah.
Okay, thank you. I just asked because your scenario considers 3 groups, but all the 3 groups have the same load. So maybe some effects will occur.
Well, it's just an example. Yeah. So in general case, this algorithm can work with other loads. But in case of this algorithm, we take into account the load generated by a single device. For example, some devices generate more frames per second than the other devices. We take it into account when we calculate the capacity for this group and this MCS. So in the end, it will result in a different capacity for these devices. Any more questions?
Okay, I guess that's all questions. Thank you, Dmitry, for your talk. The next seminar will be held at the 6th of April, and we will send you the abstract and the lecture soon.
Thank you for your attention. And if you have any more questions, you can write them by mail to me or to Vyacheslav, and we will answer them later.